All right, so parametric equations. All right, as I mentioned at the tail end of last video, if you need to brush up on the parametric notation and overall concepts, feel free to watch that review video that I put up in the Chapter 10 module. But let me just start. So instead of starting you with a definition, let me start you with a rectangular equation and a parametric equation. Let me try to sell you on the idea of why you don't want to proceed in your science, engineering studies without a good understanding of parametric, okay? Because parametric equations are far superior than rectangular equations for modeling, especially modeling like problems dealing with motion. So I offered both of these to you without any elaboration, but let me just show you. So let's assume that an object travels some type of propelled path, right? You throw a rock. Now, you got a 45-degree angle that you threw your rock, and you had an initial velocity of, let's say, 48 feet per second. Now, let's just assume, and I offer both of these equations to you without elaboration, but let's just assume that I modeled, and you could model that word problem in either rectangular or parametric. So let's assume that you can get to where I am right now. Assume you can get to here. So now, I'm trying my best to sell you on why this parametric for the rock that you just threw is far superior to the rectangular equation. So let's think about what the rectangular equation does for you. Well, again, I will kind of just do a quick sketch of this rock that you threw. Let's say you kicked it, all right? There's no initial height. There's the rock. That's a heck of a kick, by the way. Okay, so what could the rectangular equation do for you? Well, if you plug in an x, you would get out a y. Now, what does that mean geometrically? That means if you plug in, right, because this is, stop being jealous of my artistic ability. If you plug in this x value, you could, if you wanted to, find the height of your rock at some horizontal distance, right? You could find a vertical distance at a given horizontal distance. You could also plug in a y, meaning if you knew the height here, you could find the horizontal distance from a vertical distance. But you notice that what you're missing, like you might know when x is 10 feet, y is 5 feet. You might know that, but you don't know how much time it took to get to this point, right? So notice how parametric equations, they create a piecewise. So now, all you have to know is a time, in, let's say, 1 second. So if you tell me t is 1 second, I can tell you horizontally how far the rock has gone. And if you tell me t is 1 second, I can tell you at the same time it's how the vertical distance in the air. So notice that we have 3 variables, and this is kind of the beginning or the start of if you have to take a 3rd semester of calculus, which is a multivariable or vector section of calculus, that you will start to deal with what we call multivariable functions. This is a prelude to multivariable functions. And now you can see how parametric form gives more information about the motion problem, right? The projectile gives more information than a rectangular equation. So that should be enough to sell you on the idea, if you're an engineer, if you're going to deal with anything that moves, then you would probably want to at least grab a cup of coffee and wake up a little bit enough to understand what we're talking about when we say parametric equations, okay? So what is this t? So this t is what we call a parameter, and we parameterize. So in other words, we write x in terms of parameter t, we write y in terms of parameter t, and that is how we create a parametric equation. So that's what this definition of what we call a plane curve is telling you. You're just writing x as a function of t, you're writing y as a function of t. That's really what we're saying. So let's actually just jump in. First off, I will go ahead and tell you, I can't, on my calculator, I don't, at least this free version, I don't quite have all the bells and whistles. But if you go into mode on your calculator and you click parametric right here from the mode section, you can graph parametric equations. It's very nice. Now this is the part that I wish I could show you, but I cannot. So you and I assume that you already clicked parametric here, enter, and now you quit back to your main screen. So if you hit the y equals button, now normally your y equals looks something like this, right? But notice now on your TIs, you'll have y, it'll probably look something like this, y equals x equals, and then y equals x equals, and so forth. Are you with me? See how you can actually model, you can actually graph parametric equations just from your TI. Now, the only other thing to show you is, if you look at my screen here really quickly, the button that I'm highlighting here is your button that you normally use for the variable x. But if you zoom in a little bit, you see how there's also a t or a theta or an n. That same button, now when you're graphing, if you have y equals x equals, you could, when you hit that variable button, instead of an x popping up, a t will now show up. Okay, so you can put that to use as we proceed. So if you want to sketch a parametric curve, look, sketching is relatively easy, by the way. What is the harder part of it is what I'll talk about in just a second, and this is something you'll have to pay attention to. But let's start with the basics. So notice the question is, let's just sketch the curve, and the curve is described by parametric equations, right? So the real equations here are x equals, I'll get rid of the f and the t and the g, x equals t squared minus 4, and y is equal to t over t divided by 2. Okay, so there's your parametric description. Now, notice that they tell you that, and I know that yellow probably doesn't pop up very well, but they tell you that t is between -2 and +3. Now, I used t. A lot of times parametric equations are the t, the parameter deals with time. Okay, but you don't have to have a parameter that deals with time. In fact, the more natural parameter, if this would be more apparent in if you went farther in mathematics, the more natural parameter is actually arc length. But for another day. So this gives you your domain restrictions. You can't plug in 4 for t because you can only plug t values between -2 and +3, including. All right, now, so what you could do is you could notice that what they're doing here is they're just creating a table. I've already shown you how to do this on your calculator. Here's the part that so you can graph this on your calculator and see if you're getting what I'm getting. But here's the more important part. Ready? So if you plug in t values, like -2 for t, you'll get out an x value, you'll get out a y value. And you can plot 0, -1. And from 0, -1, you would get this dot that I'm highlighting right here. And then if you plugged in -1, you would get out -3, -1/2. You would get this dot here. Now here is the important part. And I'll need you to, if you'll allow me, please look at my screen. So I'm going to draw a circle. I'm going to draw 2 circles. But I want you, and I'm going to draw them slow. Let's assume that they're perfectly drawn. They're mirror images of each other. I need you to see if you can spot what's different, what I did differently. If you have to, you can rewind it, but the point is the first circle, and again, we're going to assume that these are mirror images. But the first circle, I traced moving this way. And the second circle, at least I think I did, I traced moving this way. So, right, one was going clockwise, the other was going counterclockwise. Now, this is not something to gloss over. Notice that your curve without these little arrows right here is not enough information for me. I don't know, let's assume we're plotting a comet. I don't know if the comet is moving this way or if the comet is moving this way unless you highlight that with these little arrowheads. Okay? So this is the orientation of your graph, which direction it is proceeding from. But I can show you this is not that bad. Notice how you started at -2 and you stopped at +3. So here is at -2. Notice I'm putting the dots in order. This would be -1. This would be 0. This would be 1. This would be 2. And this would be 3. So I now know how to connect my dots because I'm taking them in the order that they come, from -2 to +3. So I know that I would trace like this. Okay. Now, what I want to do while we're here is we're done with this particular problem. This one is not as interesting because notice that the domain, although they did restrict the domain, but the domain is for x is from -infinity to +infinity. And the domain for y is also from -infinity to +infinity. Although they restricted t, there are no implicit restrictions on t, right? I could have chose any t value that I wanted to. It's not like I would be dividing by 0 if I chose t equals 5. But there are, there's no implicit restrictions. There are explicit restrictions, and that's because they told me that you can only pick t values from -2 to +3. So because there are no implicit restrictions, then where I'm going to go next is super easy. So what would this equation look like in rectangular form? Right? So if I gave you, let's assume that you get to, I don't know, Virginia Tech, UVA, your engineering professor gives you this parametric description of some motion problem, and you're saying, man, let me get it back to rectangular. Let me see if I can get it back to x and y's. How would you do that? Well, it's very simple. That part's very simple. The harder part is how do you adjust the domain? So let me show you why, and that's not going to be a problem for this one. So if you follow me down here, this is how you would get from parametric to rectangular. Very simple. So here was the parametric equations. Now pick either one of those equations and solve for t. So if y is equal to t divided by 2, then that means t is equal to 2y. With me? Solve for the parameter. Then take your t and plug it into your other equation. In other words, take 2y and plug it in for t, for the x equation. And then here you go. Notice how you have eliminated your parameter. So from here, yeah, I agree with you. You could solve for y. You could do whatever you want from here. But this is rectangular. There is no more parameter. So it's very easy to go from parametric to rectangular. That's not a problem. But the problem is when it comes to how do I restrict do I need to restrict X or Y? Because, so that is where we're going right now. So notice that if you graph, and you can try this on your calculator, if you graph X is equal to 4y squared minus 4, here's what it's going to look like. It's going to look like this. Okay, so if you graph X is equal to 4y squared minus 4, then this is what you're going to get. You're going to get a parabola that extends to infinity in both directions. That is not the same. I'm going to remove my stylus here. You will agree with me that that graph that I just drew is not the same as the graph that we have. This is the true graph for this model, right? So you have to be careful going from parametric to rectangular because you need to restrict the domain, right? If you have a graph that looks like this, you're going to have to choose X values that will produce the exact same graph. Okay, that's the harder part. And if you have to, you can go back and watch those videos. But that's the part that you'll need to play with, which is what we're going to do right now. So let's take, we're now going to practice adjusting the domain. It's very simple because you now have the broad picture of how to do parametric equations, and it's very easy to just skip forward or throw out the nitty gritty of how do I adjust the domain. But I'm telling you that you have committed a error if you don't adjust your domain. I don't care about all the other wonderful work that you've done, eliminating parameters or parameterizing. All that stuff is irrelevant if you don't adjust the domain when you go from one coordinate system to another. So it says, sketch the curve represented by, well, here it is, the parametric equations. Right, so we have x is equal to 1 over the square root of t plus 1, and y is equal to t divided by t plus 1. All right, now, so that's my parametric equations. I want to graph it, sketch it by eliminating the parameter. Okay, so in other words, what this part means, eliminate the parameter, means go back to rectangular equation, right? Get it back in x and y form is what this means right here. All right, so let me go ahead and make note that for this, we can choose t values greater than -1. And that makes perfect sense because if you were to choose -1, you would be dividing by 0. Okay. So let's do that. Let's start with that process. So at this, it's your job right now to pick either one of these equations and solve for t. I'm going to pick the x equation because there's only one t variable in the x equation. Ready? So let's eliminate the parameter. So I'll give you some steps. So let's take x is equal to 1 over the square root of t plus 1. And what we're going to do is solve for t. All right, well, that's easy enough. I'm going to square both sides. So if I square the x, I'd now have x squared. If I square the 1, I'd still have 1. But if I square the square root of t plus 1, I would have 1 over t plus 1. Okay, and now I'm going to solve for t, so I'm going to multiply both sides by t plus 1. So that would now give me x squared times t plus 1 is equal to 1. Then I'm going to divide by the x squared. So that's t plus 1 is equal to 1 over x squared. And then I'm going to subtract 1. So now I know that t is equal to 1 over x squared minus 1. Okay. So at this stage, we want to take t. Now we chose the x equation. So now we want to take t and we want to plug that in for t in the y equation. The only thing that I'm going to do is, well, I'm going to show you, I'll do that on the next step. So step 2, plug in or substitute. So plug into y equals. So now I have y is equal to, well, this is 1 over x squared minus 1 over, well, can you agree with me that if I plug 1 over x squared minus 1 in here for t, the 1's would cancel out. Do you see that? So that would be 1 over x squared minus 1 plus 1. So I would be left with 1 over x squared. Okay. So at this stage, we still want to, we have solved for y, basically. I mean, or let me rephrase that. This is the rectangular equation. Now, it's a little bit sloppy, right? But do you agree with me there's no longer a t variable? So you have eliminated the parameter at this point. Only it's probably better to go ahead and do a little bit of cleaning up to get, so you would just, I'll go and tell you what I'm about to do without doing it. I would combine my fractions here, and then since this would be one fraction divided by another fraction, we would flip and multiply. And what would happen is you would be left with 1 minus x squared. Okay. So now here is the graph of the parameters of the parametric equations. If I graph 1 minus x squared, I'm going to get this. So I need to restrict my t value, right? I have to restrict my t value, so or in this case my x value, such that it matches the original graph. So in the original graph, t had to be greater than -1 so that you don't divide by 0. In this, what must x be greater than in order to get the same graph? So that third step is adjust your domain. Right, because the original, it said t is greater than -1. They gave us a domain restriction, but now we give this equation to our client. Can your client just plug in anything they want for x? No. Well, what can they plug in for x? Well, let's tell them. So in this case, x, to produce the same graph, would have to be greater than what? Have to be greater than 0. So since t has to be greater than -1, x would have to be greater than 0. All right. Now, that's kind of hard to teach. I do it by looking at the geometry. So I would look at this parametric equation, and I would say, ooh, okay, what do I need to do in order to make the, because we would have a parabola that looks like this. I would look at the graphs, and then I would adjust my domain from the graph, okay? You may do this more analytically, but hopefully that may all make sense. So let me do one more problem with you. And that problem is, this is actually really cool. I love how Larson does this. I love how Larson takes this, basically the same problem, and you deal with this problem in pre-calculus, then you deal with it in calculus 1 and calculus 2, and we're even going to deal with it in calculus 3. It's so interesting to see the various ways to solve the same problem. All right. So first I need to give you something. Now this is nestled in this description of projectile motion, but you should probably write this. So this is for projectile motion. Okay, so what is this? So this is the parametric description of projectile motion, and see if you can so for the horizontal distance, now that again, I'll read the problem just a second. You have v sub 0 is your initial velocity. So in this case, we're hitting a baseball. So how the contact we make with the baseball will be our initial velocity. Then you have theta, which is always the angle to the horizon, right? So to the ground in this case. And then you have t, which again for projectile motion you can think of it as time, how much time goes by. All right, now for y, very similar, except you would have an initial height, because unless you hit the baseball on the ground, you would have made contact with the baseball at some initial height. That would play a role in how far it travels vertically. Then you would have, again, in classroom settings, in pre-calculus, I would go through this in more detail, but you would have initial velocity times sine of the angle times t, and of course, if we're dealing with feet per second for acceleration, you would have minus 16t squared, right? If you're dealing with meters per second, then you would have to adjust that. All right, well, let me now, so this part here is just a description of projectile motion. So now let me read the problem. So it says, so we have the center field fence in some ballpark is 10 feet high and 400 feet from home plate. Right? So notice that it's hard for you to see here, but there's some fence running back here. And that fence is 10 feet high, and the fence is 400 feet from home plate. All right, so maybe you're like me, you played some baseball when you were in, I wasn't very good, but I played. So now, what happens is our player makes contact. The ball is hit 3 feet above the ground. Okay, so that's basically saying the bat makes contact with the ball right here, 3 feet above the ground. And it leaves the bat at an angle theta degrees with the horizontal. Now that they don't tell you theta yet, because they're going to tell you in part A, part B, part C. So the angle theta that this baseball makes, now you could say it's with the horizon, right? Because if this would be the horizon and this would be the angle they made with the horizon. You could also think about it from the ground if you want to think of it like this. But now with the horizon is, for right now, we're just going to call it theta. And it's the speed, in other words, the initial velocity the bat makes with the ball is 100 miles per hour. So the very first question asks us to write a set of parametric equations for the path of this baseball. And all we're doing at this stage is we're plugging in what we know into this equation. Now, the thing we don't know yet is theta. So for part A, the answer would be x is going to be equal to initial velocity. Well, that's, in this case, it's 100 feet per second. Now, actually, I almost made a serious mistake. Maybe you called it the almost mistake. They give us velocity in miles per hour, but everything else, but acceleration is given in feet per second, right? So that is problematic. We need to, if your velocity is in miles per hour and acceleration is in feet per second, then we need to adjust. So we need to adjust what is 100 miles per hour in feet per second. Well, let me go ahead and do that here. So 100 miles per hour is about 440 thirds feet per second. So now let's, my apologies. Let's plug in information that we know. So x is going to be equal to, well, notice the parentheses. The parentheses are important. So v sub 0, so initial velocity. So we want 440 over 3 feet per second. Cosine of theta, they have not given us a theta yet. T. All right, so there's x for our baseball. Now the vertical height of the baseball can be modeled as, well, let's go ahead and do this. So h, which is the initial height, which was 3 feet, plus, well, initial velocity was 440 over 3, sine of some theta, they haven't given us yet, t, and now we can just simply use minus 16t squared because now our units all match up. So we're done with part A. All right, so part B says, now they ask us to use a graphing utility to try to make this distinction, but the question is the ball going to go over the fence? Or is it going to be a home run, yes or no? Okay. So with everything else being the same, if contact with the ball is made at 15 degrees to the horizon versus 23 degrees to the horizon, are they both home runs? Are one of them home runs? Are none of them home runs? That is where we would be going with this problem. And I want to make sure you understand the question. So X has to be, now we will say that this is an infinitely thin fence. So X has to be 400 for it to be a home run. Do you agree with me there? Right? Because the fence is exactly 400 feet from home plate. And we're assuming that it's infinitely thin. So X has to be 400. The horizontal distance has to be 400 for sure. And then let's also agree that Y has to be greater than 10. Let me actually move this. So for a home run to occur, Y has to be greater than 10, has to clear the fence, and X has to be 400. Okay. So the question is, so for 15 degrees, X is 400, X is 400. Our real question is, what is Y? Okay, so when X is 400 and theta is 23 degrees, all that you're doing, let's start with 15 degrees. If you plug 15 degrees in here for theta, and my apologies, plug 15 degrees in here for theta, and set X equal to 400. You see what I'm pointing out here? Then, do you agree with me that if you know what X is and you know what theta is, then you can solve for T? Agreed? We'll do that in a little bit. But once you know the value of T, and you know theta, and you know, once you know the value of T, when X is 400, you would plug in that value here, you would plug in your theta here, and then you would look at and see what Y is. If Y is bigger than 10, home run. If Y is 10 or less, it's not. So they ask you to just look at the graph to see for this problem. So what you would find is that for 15 degrees, Y is less than 10. So this is no home run here. And for 23 degrees, Y is greater than 10. So this is yes for a home run. All right. So what I want to do now is I want to answer part D, which is the more pertinent question. So kind of entertain yourself for just a second. Let me take all of this picture. And then let's also take, let's take this guy right here. And I'll just go ahead and write plus, or no, I'm sorry, the minus 16t squared. Okay, so stay with me. We're almost done with this problem, almost done with this video. Okay, so part D asks, what is the minimum angle for a home run to be hit? Now that is a more interesting question, right? That's a more calculus-based question. So at 15 degrees, no home run. 23 degrees, yes, home run. But what is the minimum angle in order to get a home run? The minimum theta. Very interesting question. All right, well, let's let's see what we can do here. We're gonna work. I've already alluded to this in the previous page. What we're gonna do here. So we're gonna let x equal 400. We're gonna let y equal 10, and then we're gonna start to do some math here. So our first goal is we need to figure out the t, the time, right? So x is 400 or y is 10. I know it has to be bigger than 10. I know that, but hold on. So let's do our x equation. So I would have x is equal to, so I know x is 400. So 400 is equal to 440 over 3 cosine of theta t. Now, what I'm going to do, and I'm going to do a lot of this without showing you the nitty-gritty details, but I'm going to solve. I've plugged in for x, and I'm going to solve for t. I don't have a theta, I don't have a t, but I'm going to solve for t. So this is the part that I'm not going to take time to work to show you. So t is equal to, well, it's going to be 400 over 440 divided by 3, which basically means t is equal to 1200 divided by 440 cosine of theta. Okay, so you're able to solve for t. Now, using the fact that y is 10, we're going to be substituting 10 in here for y, and we're going to be substituting, I drew this in the wrong spot. Let's do that again. Substituting 10 in for y, and substituting 1200 divided by 440 over theta in for t here and t here. All right, so that I'm going to write that. So that's what's going to happen right now. So we would have $10 is equal to 3 plus 440 over 3 sine theta. And now instead of having a t, we're going to plug in the 1200 over 440 cosine of theta. Minus 16, again plugging in. So 1200 over 440 cosine of theta squared. Okay. Now, at this stage, this is the part that I'm going to tell you, but I'm not going to work out all the details. At this stage, you're going to need to first do some combining. You're going to end up, you'll have a sine over a cosine, which you could turn into tangent if that would make it, that's what I'm going to do. And then you would have a 1, basically you would end up with, since 1 over cosine is secant, you're going to end up with, but it's squared, so you're going to end up with a secant squared here. All right, and then obviously if you subtract 3 from both sides, you'll end up with a 7 on the left. So a little bit of manipulation would get you to here. So 7 is equal to 400 tan of theta minus, now all I'm doing is I want to use some identities so that I can solve. So minus 16. All right, well, I have 120 over 44 squared. Where'd that come from? Well, if you have a 0, 1200 in the numerator, 440 in the denominator, so these zeros could cancel. That's where the 120 over 44 comes from. And then 1 over cosine is secant, so 1 over cosine squared is secant squared theta. Now, what is secant squared? What is an identity for secant squared theta? Well, that's just tan squared theta plus 1. So I'm going to be plugging in a tan squared theta plus 1 in for the secant. In fact, I'm actually, since I'm running out of space, what's gonna happen is I'm gonna plug this in for secant squared. I'm just gonna erase secant squared in just a second, okay? So I'll hold this here for long enough so you know what's gonna happen. The secant squared is about to become tan squared theta plus 1. So there it is, tan squared theta plus 1. All right. So remember, your goal is to solve for theta. So you're now going to have to start to group together. You're actually in actuality, you would want to use a quadratic formula in this case. You would set this equal to 0. Right? So I can, if I had a 7 there, don't you agree? So if I subtract 7, I would have it set equal to 0. And now listen to me. You would distribute out here. Then you would combine like terms. And when all is said and done, you would end up with a quadratic, right? Whereas I'll go ahead and tell you. So in this, with the quadratic that you would be left with, A would be whatever is attached to the x squared, which in this case would be the tan squared. A would be equal to 16 times 120 over 44 squared. The B would be equal to whatever is attached to tangent, right? Ax squared plus bx. So in this case, whatever's attached to tangent. Now once you set it equal to 0, you would have, let's see here. Yeah. So you would have a positive 400 here for B, and then C would be equal to negative 7 plus, well, you got whatever you get when you distribute, because you'd have to distribute this to 1. All right, so whatever that is. So I'll just put a placeholder there. Okay, well, I know you don't like that. But when all is said and done, whether you do this a different way, you would end up with basically a theta. You would know what tan is equal to, and then when you take tan inverse, you would get roughly 19.4 degrees. So if you make contact with that baseball with all those conditions at 19.4 degrees, you would get a home run. Okay, I know I left a lot of details out. Notice the details that I left out were not calculus details. In fact, I would love to be able to show you how to do this with calculus as opposed to doing this with algebra. But we are not at multivariable calculus yet. So you could think about how you could take a derivative of that, because that is an optimization problem. Just not a problem for this video. All right, so I will see you in the next section, and the next section is we'll actually start to do some calculus in a calculus class, right? We're going to do some calculus of parametric equations. See you there.